Hey everyone, I am Vibhu, and this is my project under my coursework EC208 under Dr. Amareshwar sir. So today we'll be looking at RETINEX based low light image enhancement, and this is what I've chosen. Let's look at this. So I just want to introduce myself. I am an aspiring amateur photographer, and this is some of the pictures I took, right? So this is from an art form called Yakshagana that is done near coastal Karnataka. And when I see pictures like this, right? If you can see the two, I've slightly enhanced the right one. And being an electronics engineer and a photographer has like it makes me curious to see how exactly this enhancement is being done, right? Which is why I picked this. And Retinex is one such algorithm that helps us do it. But what exactly is Retinex, right? So, Retinex was coined by Edwin Land in the 1960s, where it basically means retina plus cortex. And the story is pretty curious, actually. So, what he did was he had a green apple. He like shined red light on it, and went into the room, right? And there he made a curious observation. The human eye does not, visualize that as a red apple, but it understands that it is a green apple. And he was like, why? Whereas if you took a photo of it, it would appear to be a red apple. So he assumed that, the human eye sort of knows and predicts like the difference between the light that is shown and whatever is actually present there. And he didn't know where this, mental calculation was happening, which is why he termed it as retina plus cortex, as in the math he assumed to be happening there. And this equation is the exact replica of it. Let's say you have the image s of xy. You want to convert it into its reflectance, which is the accurate color values of it, and the illumination, how much light is being shown on it, right? And if we see the pictures on the left, this is what's being done. The upper image is the original, whatever we see normally. The lower is the distributed reflectance, and I is the illumination. Okay. Now, so our goal today is to kind of eliminate illumination and solely get reflectance, right? Because if we look at this picture, illumination is the darkness present here, the light present here. We just want the colors, the details, and once we have that, we'll be able to like upscale it much better, right? So when we come here, it's in multiplication right now, and mathematically it's very hard to compute. Like computers find it very hard to compute this multiplication math. Addition is much simpler. So we do one thing. We convert it into the log domain, right? So we take log s and we do this. And again, I'll come back to this. Our goal is to find r, the reflectance. But to do that, we need to know what I is, your illumination. And let's ask ourselves, right? What exactly is illumination? It's how much light is present in the image, right? And so there's multiple ways to find this illumination. This upper thing you see here is the Retinex algorithm. And how you find I is a subset of which Retinex you're using. Here we'll be using single scale Retinex, which is the simplest form, to get an understanding of it, but there are much more complex ones. I'll talk about it later. So how do we find I? So in single scale Retinex, there's a clever way where it's called Gaussian low pass filter. And this takes advantage of the fact that light is low frequency, in the sense if you look at an image, light does not change rapidly between different pixels. The object itself does, as you can see here, this black and white, like very drastically. But let's say you kind of shine the light on this, it would spread evenly throughout the image, and that's why it's low frequency, as in it spreads uniformly. And so now why Gaussian? So what Gaussian does, it's an averaging kind of function. This is sigma basically. So we have a kernel, right? We pass this kernel, we convolute it with your original thing, and yeah. So the middle value has the highest peak, and it averages with the surrounding pixels that are present there. I'll talk more about Gaussian, the low pass filter, in the next slide. So this is the equation that we'll be using today. And one second. Yeah. So g of xy is equal to 1 by 2 pi sigma square e power minus x square plus y square by 2 sigma square. So let's look at the properties of this first, right? First of all of these are positive, right? Um, yeah, so first of all of these are positive. Second of all, the area of the entire thing is 1. This is very crucial, I'll explain in a bit. But first let's map this to this kernel that's present. Now the center of this kernel will be your x comma y is equal to 0, and this is, you can think of this as a 2D map, and each point here will like we can substitute values of x comma y here and put this in, right? So for x comma y is equal to 0, this will be 1 by 2 pi sigma square, right? And so it'll start decreasing on the way out. Now I mentioned why the area of this has to be 1. Okay, let's look at a plane image, right? Let's look at this is my image matrix, and let's say it's very plain, right? It's only one color. Now let's say we convolute it with this Gaussian filter, and we do the average of each pixel, the convolution, addition, everything. What happens is your overall pixels get brightened up, and that is not fair, is it? Because we don't want to change the lighting of the image. We just want to get whatever was there, like present. So we should expect to get the same image back. And this is why the area of this has to be 1, right? To keep the energy of the image the same. And how does this make, how is this low pass? So what does low pass mean, right? Low pass is in it blocks the high frequencies and lets the low frequencies go through. And when we looked at g of xy as an averaging, this already means that you're sort of blurring it, and blurring in this context means it's a the frequency is becoming low pass. Like I said, light is going to change from one pixel to another very gradually, and this is what makes it low pass. It When you do the convolution with your kernel, you are effectively blurring out all the high frequencies that exist because you're taking an average of them, right? Um, yep. So this is, I think, one of the coolest parts that we've come to, implementing the actual SSR on the initial image, right? So I've done the math that I've just explained to you. Sigma here is what this is. So let's look at this thing again. A higher sigma indicates that it's more concentrated to the center, meaning there's not much averaging going on, and a lower sigma means it's more distributed, and we can see that here as well. So let's first of all let's appreciate the beauty of this. Here you can't even see the this guy's face, but if you look at these pictures, it's so clear and visible, and all the illumination, the lighting of it has effectively gone, and you're left with the the color parts and the details of the image that are left. So let's talk about how this changes with sigma, right? So sigma is 20. That means there's less averaging. It's more contrasting, and this is sort of why we lose depth and clarity as well. And if you see sigma is equal to 400, it's more blurred out, if you can see. Okay, let's move on to the next one. So I'll just be explaining what code I actually ran here. I used OpenCV as a library and NumPy. Now what is case size? So depending on my sigma, I need to get a matrix which accurately reflects the tiny minuscule details between one pixel to another, right? So if I had only a 3 by 3 matrix for a very large sigma, then effectively it would just be 1 and 0, and that would not give a smooth averaging filter, right? So I need a bigger kernel, and this is what the k size does. It makes your kernel bigger. And the Gaussian blur, I think this is pretty self-explanatory, but there's an interesting caveat to this as well. And that is convolution in math is time-taking and very long. But you know what convolution in the frequency domain is? It's nothing but multiplication. And we, exploit this to the maximum. We convert whatever math is here to to a frequency response. And how that's done is, when you do your fast Fourier transform, your xy plane, right, it becomes a UV frequency axis. So your lowest frequencies are put into the center and your highest frequencies are put into the corners. And the same thing is done with your original image. And now you send this kernel, frequency kernel, you just multiply all of these and it happens like pretty much instantly. Fun fact, I tried the convolution first and I ran the code for 30 minutes and it still didn't give me an output. But when I changed to fast Fourier transform, it was pretty much instant. Fine, so this is what your Gaussian blur does, right? And SSR. So now the Gaussian blur has given you your log I, right? And now we want to get your log R. How is this done? Log S minus log I, simple. And we need to get R back, so we just do the inverse log of it. And this gets all of that done using the help of the NP library. Yeah. Okay. So we looked at this, how we're losing a lot of color here, so that's pretty dissatisfying. But also keep in mind, this is the lowest form of RETINEX. This is single stage RETINEX. So it is pretty elementary, but you can still see how good the clarity of this is, right? So there's obviously better models, and unfortunately I won't be able to explain it here. It's out of the scope. But for for fun, I've just implemented it and shown it here. So this is called multi-scale with color preservation, right? These are some different complex RETINEX models, right? So there's multi-scale, there's color preservation. GIMP and NASA actually use very high modified RETINEX versions of this. Like for star imaging and all, they did use RETINEX. So it's a very popular algorithm and it's very cool too. And you can, see how well this is enhanced, right? The details are right there. And yeah, it's really fascinating to me, like when I was working on this project as well. Observing this for the first time and seeing this live in the picture was really cool. I didn't expect it to be this great. Anyways, moving on. These were the references I've used. Thankfully, this has been documented quite a bit. In my personal, projects, I want to implement like the higher, more complex versions of this. There's some deep learning aspects that we can use as well. But for now, for this, I've used this GitHub repo. It's been very well documented. I was able to understand quite a lot. And there's this research paper as well. Do check them out. Now, so that is pretty much the end of my presentation. Thank you so much. If you want to just talk about this, or just contact me, contact my email ID, just send a mail. I'll respond to it. Thanks.